So the other drawback of solar design tool is it does not do shade analysis. Trees are tricky, and not being able to model shade because of trees can land you into problems. So it used to be we would get up on the rooftop with a survey tool, and it would kind of read a chart and let us know, when the sun's going to shine and when's it not. You can literally just carve out, based on where these shadows are, a percentage of your solar production um, for shade analysis. Now, a detailed shade analysis done in a computer environment would actually be calculating the energy on the solar array at every hour of the day and giving it to you in a very detailed, granular report. The most accurate shade analysis softwares are found to be as accurate as going to site and doing a shade analysis. I actually think they're more accurate because, again, trees grow over time, and so modeling the tree growth is better done in a 3D environment than a 2D environment. So Helioscope is a software that is kind of the most popular um, solar design software on the market, I'd say. I don't actually know numbers and usages, but that's just the feel I get. So, they've been on the market a while. They have good following, and they have a very rapid interface. What this is showing is some of the advantage of a 3D shading model. This is with the tree there, and what's interesting about this image is it shows that it didn't really matter if the modules were facing north or facing south. The panels that were closest to that tree were the ones that were less productive. So these southern facing solar panels on this southern facing rooftop produce less energy than these northern facing solar panels because they're shaded by that tree for a substantial portion of the day. And so now we've said, okay, well, if the homeowner must not chop down that tree, maybe we just stick to the sections of the roof that are furthest away from the tree in order to get the most amount of production from that rooftop. And so Helioscope is doing, wire sizing and voltage drop calculations. Maybe not to as a detailed extent as other software. So they're really trying to stay focused on preliminary design and kind of assuming detailed design will come later. What that might mean is you do your shade assessment in Helioscope, and then once you know your final array layout, then go replicate it quickly in another design software for permitting, like Energy Toolbase. One interesting tool that Aurora has is taking a stab at making a hourly load profile to say this is how we think the customer uses their electricity without knowing that this is how the customer uses their electricity. And so the way you do that is you take your monthly consumption data, and then you say, okay, well, that has to be consumed by a 24-hour time frame. And then they have a survey that says, okay, what electrical devices are in the home? And so they kind of assume that if you use air conditioning, it's going to be on toward increasing as the day gets hot. If you have electric heat, your winter load may look closer like this. Depending on your region, your if you have a swimming pool or not, if you have an all electric home or not, these load profiles will jump around. So they use that for their own economic analysis. And so what we're going to do is look at a couple of these design softwares and see kind of how quickly they could be modeled. So why don't we start out with Well, we were just talking about Aurora, so why don't we start out with Aurora? And I'm gonna like kind of skip through the video and just kind of tell you what's going on. You know, here they're modeling consumption data, which is kind of interesting. You have the option to input a few different kinds. The more granular your data, the better. Um, but now we're in the good stuff. Now here they're having their residential site, and so what's nice about Aurora is they already have some uh, templates built in for making the roof drawing process go a little more quickly. And we're just clicking on the edges. And so we can see how it's just been kind of, auto detected. Um, at that point, you're kind of basing your model. If you didn't have LiDAR data, you'd be using the street views and aerial views to kind of, wing it and kind of eyeball it. If you've measured the roof slope, well, there we have it with the LiDAR data. You now can just grow your model to fit the LiDAR data, and it will just match up, nice and perfect. So they have different shapes of trees to make your 3D shape a little bit better. And then here they're drawing obstructions. And so now they're doing a shade analysis. And so obviously the south side works well, and the north side is the least sunny that I do. But we can also note just how large this area around the chimney is, and so we can kind of say, okay, well, is that going to be, if I stay out of this area, maybe I just want one array surface, or knowing that I'm going to have a broken array surface if I go into this larger area. Previous examples, they're selecting their module, they're selecting their inverter, and it's doing the string sizing. And because it is truly building a 3D model, it will be calculating the voltage drop for every single panel on the roof. They have a very robust, very strong kind of engine. This is an even more difficult, complicated roof. So, um, getting those inverted those folds, uh, seamlessly transitioning from one layer to the next. Okay, let's get into the actual model here. So now they're breaking the roof into sections. They have this smart roof system where you're kind of telling what feature the roof has. And so they have a feature for this inverted fold roof style, and they apply it to the shape. And so, assuming you know what you're doing, even a very complicated rooftop, even adjusting the image slightly to make sure they're in line. And getting it precisely matched up. And now they're building a little awning off the back porch. So they're saying no, it's a different shape than our previous roof. So they've taken out some roof planes and are just playing around with the slope a bit. And so now they have a very detailed 3D model of the roof. So from that point within Aurora, you start defining your field arrays. You start putting your modules together, and they'll have a one line diagram. I think what they're showing in this picture is that they're importing this to do roof designs based off construction drawings, which is not always quite as easy as it sounds. There can be some guesswork in there. And so Helioscope has near maps built into it, and near maps is a you just get a better resolution than what you get on Google or Bing. I'll usually go over to Bing and use Bing images, which is Microsoft's rival to Google. They're a little bit more clear, but Near Maps is pricey, and it has the best images. And some of the commercial design software integrates Near Maps into it. The cheaper design softwares like Solar Design Tool, you would have to pay for that near map image. And so they're defining their array layouts and kind of showing off their fine tuning. They're showing landscape versus portrait, versus kind of the staggered approach versus not staggered. Staggered, it looks pretty good. Although I like the I like my arrays to be rectangles because solar's rectangular. I don't like asymmetric solar arrays. Rooftops sometimes aren't symmetrical either. And so Helioscope, even though the interface as opposed to Aurora, Aurora, you build the 2D model, then you tweak it a lot in a 3D view. Helioscope, even though it has LiDAR data, and even though it's building a model, it's kind of more focused on working within this overhead view. And so it still has its 3D view, or its 3D model behind that. Maybe they'll... Here they're doing a shade analysis, and what they're finding out is, actually, on the side near the kind of southeast, doesn't actually get that much sunshine. That maybe these trees over on the left-hand side are kind of less important. And they're locating their inverters and kind of finalizing their design. And so even though they can be doing very detailed performance estimating and calculating your links of home run conductors and voltage drops of the home run conductors, they're kind of stopping before they become full-fledged construction documents, and sometimes that can get a little annoying when you're doing commercial projects and the developer has only done a helioscope design and they just use that to go out to bid. There's a lot of open scope in there that they're not planning around, like the true nuances between running home run conductors and conduit throughout the array or going into a cable tray. That kind of stuff should be pointed out on a detailed construction document. You're not going to get there with helioscope by itself. What helioscope is much more focused on is being a very accurate shade analysis tool, but also one that is more rapid and focused around getting that number. Whereas I'd say Aurora is trying to build something that's a little bit more comprehensive, a little bit more expandable, has a little bit more bells and whistles, a little bit more finesse, and that takes a little bit more time too. And while they might overcome it with features you won't see anywhere else, particularly for 3D modeling difficult residential rooftops, um, Helioscope is saying, well, our platform is super easy for doing kind of commercial layouts. And so now they're doing the clearances around electrical equipment, 6 feet off the edges of the roof on a flat roof, 4 feet around your electrical equipment, and then you know then there you go back and give the array a little bit of a haircut for modules that don't really need to be there to make the install a little bit easier. And so both Aurora and Helioscope generate single line diagrams, and Helioscope and Aurora's single line diagrams are very detailed, but in a sense they're still kind of basic. They're intended for you to take that and export it into your own gingerbread, and even though they're doing voltage drop calculations, they're not necessarily going to tell you your conductor. How do you determine how many solar panels go onto a particular circuit when they are wired up to a particular inverter? Inverter manufacturers provide online software to assist this design process. They take the specific information from the module specification sheet, such as the voltage and amperage and temperature coefficients, and use that information to suggest configurations which are compatible with their product. So close examination of the PVWatts data can tell us the maximum inverter size without overspending on inverter capacity. Typically, inverters are 10 to 20% undersized compared to the solar array nameplate capacity, although oversizing as well as significant undersizing is not unusual. Solar cells are pre-packaged into solar modules, which is the industry term for a solar panel. And circuits of solar modules are labeled by the industry jargon as strings. So there's an inverter called a string inverter that at the residential level is simply one inverter for the entire system, with the inputs being multiple circuits or multiple strings of solar panels. The opposite approach is to use micro-inverters, where there's one inverter being installed behind every single module on the roof. Micro-inverters are particularly interesting because they produce AC output instead of DC output right up on the roof, eliminating the DC home run cable requirements, which require metal protecting the home run circuits, which I think is nothing more than DC discrimination, because the metal is only there for physical protection, so there's no reason to differentiate between an AC source circuit and a DC source circuit, but that's a digression. The third inverter approach, other than string inverters or microinverters, is the most popular approach for rooftop solar, an approach called DC optimizers that is somewhat a mixture between string and microinverters. DC optimizers, like microinverters, put a box behind every solar panel on the roof, but unlike microinverters, it only regulates a DC to DC voltage output rather than doing a full DC to AC conversion on the roof. The DC to AC inversion still happens, but it happens at a string inverter located further down the line, typically on the ground. This string inverter has less stuff in it because the voltage regulation on the DC side has already been controlled and optimized up on the rooftop. But this architecture is still slightly less expensive than installing a full microinverter behind each and every solar panel on the roof. Both microinverters and DC optimizer systems are more expensive than string inverters by themselves, but either of these systems is more accommodating than string inverters for shade. And so either microinverters or DC optimizers should be selected when there is any shade on the roof. Of course, shade and solar power do not mix, but partial shade, such as a single tree shading a portion of the array in the morning or evening, can be substantially mitigated through the use of these products instead of a string inverter by itself. Some installers do not like DC optimizers or microinverters because these platforms put more electronics on the roof than string inverters do by themselves, and those electronics can and do fail with time. If a single microinverter or DC optimizer fails on a roof, the most cost-effective answer may be to leave it alone until there is another good reason to get up on the roof, rather than incur the cost of replacing just a single failed unit, a solution that a client may not always be so pleased with. In the absence of shade, which system is better is a matter of opinion. Without getting too nuanced, I'd recommend microinverters for do-it-yourselfers, DC optimizers for experienced installers, and string inverters for ground mounts. National Electric Code requires solar conductors to be de-energized on command, and a strict interpretation of the latest National Electric Code would mandate the use of DC optimizers or microinverters when solar is installed on the roof. There is no off switch to a solar panel, and so module-level panel electronics are the only means to completely isolate the solar array during an emergency and bring the system voltage down to a safe voltage. So on a roof, it is wise to use module-level panel electronics despite the added failure points and slight cost increase. On the ground, detached from the building, the use of module-level panel electronics, particularly on an unshaded solar array, is less important. Regardless, the circuit sizing process between the solar array and the inverter is useful to know how to do. Because microinverters are module level, microinverter manufacturers typically provide a compatibility list or calculator, which essentially tells the user which microinverters are compatible with which solar panels. The microinverter specification sheet will then reveal how many microinverters can fit on a given circuit. Microinverter design is flexible, and any regular electrician with AC experience will feel comfortable installing them. In this example, a microinverter can have up to 16 microinverters per 20 amp branch circuit. If a pallet of solar panels is 25 panels, the system would require 2 branch circuits of up to 16 modules each. One circuit can be a different size than the other. It doesn't really matter which direction the modules face, even within a circuit, because the microinverters allow each panel to operate independently of its neighbors. Experienced solar installers will opt for DC optimizers with string inverters, which brings the code-compliant and shade-tolerant advantages of microinverters along with some cost savings. Microinverters cost more than DC optimizer solutions. The compatibility of a solar panel to a particular DC optimizer is similar to the compatibility of a solar panel to a microinverter. It is simply a matter of solar panel voltage compatibility, and can be determined by using the manufacturer provided sizing resources on their website. So I will demonstrate string sizing first, and then illustrate how it applies to DC optimizers specifically. Fronius makes a popular string inverter, and their sizing process is similar to other manufacturer string sizing software. The solar module is selected along with the inverter. Typically, string inverters are 10 to 20% undersized compared to the nameplate capacity of the solar array. This is because the size of the array is the input, whereas the inverter capacity is the output. There are losses between the input and the output as much as 20% in the summertime due to heat alone. Again, these losses are modeled in PVWatts, and so the exact relationship between the DC input size and the AC output size can be closely examined within PVWatts. But the short of it is that the AC inverter is commonly undersized compared to the DC array size, although it doesn't have to be. So for one 8 kilowatt pallet of solar modules, you might look at inverters sized between 6.5 and 8 kilowatts. At any point, the solar panel and inverter are selected along with local record cold and average hot temperatures, and then the manufacturing sizing software will reveal all the acceptable wiring configurations of the components involved. Most string inverters today have multiple circuit inputs capable of operating independent of the other respective circuits. So even on a string inverter today, it's possible to have two circuits of 5 to 10 solar panels alongside one circuit of 7 solar panels and another circuit with 10 solar panels. Just as an example, higher end inverters have multiple maximum power point tracking circuit inputs, such that shade or mismatched orientation of one string or circuit would only impact that specific string and not pull down the rest of the system. This is an advancement from string inverters of years past, where all of the solar panels on the system had to face the same direction and have the same number of modules per circuit without any shade at all. For inverters with multiple power point tracking, circuit sizes can differ from one circuit compared to the other. Similarly, a DC optimizer or micro-inverter system can be thought to have one maximum power point tracker for every solar panel on the roof, such that each solar panel is its unique system. So circuit design with module level panel electronics has greater flexibility than circuit design with string inverters alone. Within a single maximum power point tracker, whether it be a circuit or one solar module, all the cells have to face the same direction. So say a pallet of solar has 25 panels. This string inverter could accommodate 2 circuits of 8 solar panels facing southeast on one power point tracker and 1 circuit of 9 solar panels facing southwest for a total of 25 panel system working on one single string inverter with 2 maximum power point tracker circuits. DC optimizer sizing is similar to both string and microinverter sizing. Here is a 132 panel layout using some oddball thin film solar panels with a atypically high voltage and atypically low amperage compared to standard solar panels. The string sizing software suggests that for this 132 panel thin film system, for this 20 kilowatt array, to use 2 10 kilowatt string inverters distributed between 6 total circuits using the P405 model DC optimizer. This is further confirmed by the specification sheet, which reveals up to 25 modules can be added to a given circuit with this particular P405 optimizer. DC optimizers work by increasing the panel voltage and decreasing the panel amperage. This allows longer circuits than standalone string inverters or microinverters to be used on site, as more power can be pushed through the same size conductor, again because the voltage has been increased to its maximum operating capacity, thereby decreasing the amperage, and because the constraint on the cable is most likely the amperage capacity of the cable. At that point, by lowering the amperage, more panels can push their power through that same similar conductor. So as an installer, I like DC optimizer installs because of their long circuit links where all the panels are pushing their power through that one conductor, which means simpler wire runs from the rooftop to the ground. Now that we know the number of circuits the array will have, the next design step is to identify where the starting and stopping point of each circuit will be. This information is useful in determining where the home run circuits between the solar array and inverter will land up on the array on the roof. Special care should be taken during installation to make sure these circuits are plugged up correctly. Having these locations planned carefully in advance will reduce mistakes in the field. I locate these connections at the corner of an array so that if they ever need to be inspected in the future, they are easily accessible. There are two approaches to circuit layout. I think it's best to go for a simple, logical circuit layout, even if it means using more circuits than necessary on the roof if those circuits start and stop in logical places. For example, starting a circuit on one side of the array perimeter and ending the circuit on the opposite side, moving across the solar array in a straight line, is a logical, straightforward circuit layout. The alternate approach I call snakes in a basket, where the circuits randomly start and stop as a winding circuit path is drawn throughout the array. So the first circuit starts here and ends here, and the second circuit starts here and it ends there, resulting in a compact circuit design where the starting and stopping points of the circuits from a zoomed out view are randomly distributed throughout the array layout. But if that circuit map is not available, servicing such an array could become hellacious. So clear, logical circuit layouts keep it simple enough for a field solar installer to visually inspect the array and figure out what's going on with the circuits through visual inspection. Interconnection options are available either as a load side or supply side connection. The supply side connection is located between the customer meter and the main service panel. The supply side connection can equal but not exceed the rating of the electric service. That means if the site has a 200 amp service, then a 200 amp energy system can be connected to it. After all, the conductors feeding the building are rated for 200 amps. Regardless of whether the power to the building comes from the solar array or the utility, the power is still throttled by that 200 amp main breaker at the top of the electric service panel. Alternately, a load side connection can be selected. The load side amperage allowance is less than the supply side amperage allowance, and so is generally selected for systems which will power less than 100% of a building's energy. whether it be a small battery or a small solar array. As a starting point, National Electric Code dictates a 200 amp electric service cannot be fed with more than 200 amps of power, whether it comes from the utility through the main breaker or from the solar array through a load side breaker or any combination thereof. In other words, if a 200 amp service panel has a 200 amp main breaker, then it has 0 amps available for a solar load side connection. Obviously, this is not the case for solar, and National Electric Code allows an exception. When the solar breaker is located at the opposite end of the bus bar from the main breaker, rather than inserted somewhere in the middle, so if the main breaker is at the top of the panel and then the load side solar breaker is located at the bottom of the panel, an additional 20% amperage allowance can supply the electric service panel. In other words, a 200 amp electric service panel can be fed with 240 amps of power divided between the utility main breaker and the solar array. This could be 200 amps of utility power and 40 amps of solar, or 180 amps of utility power and 60 amps of solar, or any other combination. It's allowed so long as they are located at opposite ends of the bus bar with all of the load in between. This code provision is necessary because it is common to have more than 200 amps of load breakers on a service panel. If you count the breakers on an electric service panel, it's likely to total 300 amps or more. An assumption is being made that not all the loads are being used at the same time. If 300 amps of load were pulled through a 200 amp electric service panel, the panel would heat up and start a fire. The 200 amp main breaker is there to prevent that from happening, but now solar is also feeding the panel from the other side of the bus bar, and so the panel can potentially draw more than the 200 amps of power that it's rated for, which might be a fire hazard. Code allows the extra 20% amps capacity when solar feeds the very bottom of the bus bar, not because it's being nice, but because when solar is landed at the very bottom of the bus bar, the actual cross-sectional area of the bus bar that the current is physically traveling through will still not exceed 200 amps, because the electricity from the solar array will not combine with the electricity from the main power supply before flowing into the load, because in the exceptional case where you get the extra 20%, all of the load is located between the two power sources. If the solar array were landed anywhere else than on the bottom of that service panel, potentially its power supply could combine with the grid to exceed the rating of the bus bar by supplying 120% of the amperage through a cross-sectional area of the bus bar. And so this exception is only made when the two feeders of a panel are located at opposite ends of the bus bar. So the takeaway is either the solar array will land between the utility meter and the main breaker as a supply side connection, such as for a larger solar array or for multiple solar arrays alongside battery inverters. For this reason, I recommend installing a 200 amp disconnect switch as well as a dedicated electric service panel, which will be adequate to prepare the site for future expansions, such as the ability to combine solar with batteries to run the home off-grid during a power outage. But if simply offsetting the electric bill is the goal, Easier project logistics can result from simply landing the solar array or the battery inverter or both at the bottom of the bus bar. A supply-side connection requires a power shutdown from the utility. A load-side connection does not. But even for small interconnections, supply-side connections can be made. Sometimes the inside of the building's electrical system, quite frankly, can be a mess. A supply-side connection made outside the building where the electricity leaves the meter and enters the building can keep the system inspection outside the building. Here is a small commercial electrical room. How are we going to interconnect into this system? The room is surprisingly code compliant, other than the fact that this space in front of the electrical equipment should not be used for storage, but the room is messy. The last thing I want to do is bring in an inspector inside this room. Now, back on site, we look outside the building and we see where the electric cables leave the meter and enter into the building. The supply side connection will intercept and tap onto these conductors at this point. Now, currently, there is an electrical box called an LB where the cables enter the building, feeding the two separate 200 amp panels coming out of this 400 amp meter base. Ahead of the array installation, the electrician had the utility power down the building. The building service entrance conductors were then pulled out of the electric service panel, out through the LB, and back to the metered connection. The LB was then swapped out with a larger junction box, and the conductors are then routed back through. This process was scheduled when the building was not in use, and it took less than an hour. So when the solar array was ready to install, all that was needed to be done was to open up the junction box and tap onto the conductors, a process that took only a few minutes. Minimal business activity was interrupted as a result of the supply side connection. Tapped conductors are still needed to be protected by overcurrent protection, so installation of a service panel with breakers is necessary, or something more simple like a fused disconnect switch. The conductors are tapped using tap connectors in the junction box. Here's a cable going into the service panel on this commercial project example. Pierced insulating tap connectors were used instead of standard tap connectors because the piercing insulated tap connectors install faster. Standard tap connectors require cutting the conductor and stripping back the insulation jacket, bending the conductor wire, and other small tasks which require time and hand strength. The piercing insulated tap connectors simply crank down onto the conductor, but if the building can sit without power for a couple hours, most electricians will prefer to use the regular tap connectors where possible. Regular tap connectors are less costly and easier to reconfigure at a later date than their piercing insulated tap connector counterparts. In the same screen we get the array layout. We also have the string sizing built in. This is just like a manufacturer string sizing tool that you would find on a manufacturer-specific website. For example, in other programs, here we have Fronius's string sizing tool, and picking out our inverter and picking out our solar module will give us a variety of different options. In this example, we could have 2 strings of 11 or 2 strings of 8, and you would have to figure out in my array layout what string sizing or string configuration would make the most amount of sense. Well, in our solar design tool presentation, that string sizing capability is built right into the software. And so here we've selected a solar panel and in-phase micro-inverters. And for this particular micro-inverter, it has a maximum number of modules per circuit is 17. And right here in Solar Design Tool, in the design software, we're being limited to the microinverters capabilities, microinverters. But Solar Design Tool has a plethora of kind of final design detail documentation, more than any other, really any other software. It provides the most detailed out of the box one line diagram, um, which is pretty impressive given that it's kind of on the low end of price, with the caveat that its tools are really geared towards small residential projects, 4 circuits or less. In general, sometimes I'll model larger projects and then kind of stitch them together in CAD afterwards. But once the design is put together, you can go back in and modify things like wire sizes, connection versus load side connection. It's common to do either or. There's certain situations when one's better than the other. Uh, but it's nice to see that detail, whether or not there's a production meter, interconnection meter. This is a pretty detailed interview. And if you're hiring out to a third-party CAD service, if they don't have this level of detail, then they're not going to be able to give you a thorough electrical drawing. And so here we are. It's modeling is our sub panel with the microinverters all landing on different branch circuits, and then tying into a solar production meter, going through a main disconnect breaker, and then heading out to either the utility main service panel or the utility meter, because it's been denoted as a supply side connection. So these one line diagrams do get automatically generated at some point in the chain. Where some of these line diagram creation tools fall short is the balance of system material wanting you to detail exactly what it's going to be out in the field in construction. So for instance, here's a popular rooftop transition box that's for transitioning the cable to go down into the attic, and being able to interrupt these home runs and say, no, 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 right here, I want a junction box to transition into the interior of the attic. Sometimes that level of detail needs to be kind of re-highlighted in CAD. We are noting, based on earlier where we specified the location of the meter and the location of the sub panel, where we're specifying circuit detail, what is the conduit run going to be in, how long are those runs, what are the voltage drops of the runs. So these runs are all of equal length. You can go back and adjust that to be more accurate. At the end of the day, Solar Design Tool connects all those dots together to tell you, okay, you use this many feet of cable, this many feet of conduit, here's the voltage drop. They're actually the only, well, we'll get to that in a minute. So here's an example of a conduit schedule where, I know the print is fine, but it's telling you, you have a combination of 3/4 inch and 1/2 inch and 3/4 inch conduit. You might go back into this software and say, okay, it's all going to be in 3/4 inch. So we're going to upsize our conduit, and that'll change your conduit fill calculations, and gives you a good glance at your balance of system material as well. You might be looking at this material list and saying, well, why don't we simplify it? And sometimes you can oversimplify, like using number 8 cable for every circuit just to only have number 8 cable. That could result in you spending too much money on your cable budget. But if there is just like one oddball saying, okay, well, there's 2 circuits of 12 and 1 circuit of 10, but look, this circuit of 12 actually has some voltage drop to it, and so let's make it a circuit of number 10 AWG instead, and for voltage drop mitigation, and then even though this particular circuit maybe has fewer optimizers or fewer microinverters, so less current going through it. It doesn't have much voltage drop at all. But let's go ahead and make that number 10 as well, just so that these conductors are uniform. This is a one-line diagram that was created as a result of this kind of survey process, all by computers and surveys. There's no one hand drawing this. It's not like I fill out a survey and overnight the design to the designer who squirrels away overnight and he hand draws this. This is all computer generated and CAD exportable. And Solar Design Tool is the only one of the design softwares that I know of that has the balls to give you a National Electric Code report of calculation after calculation that you can just print out and staple and include with your permit package to say, hey, look, we've evaluated the design from an electrical perspective. It's really trying to be a permit company. So it's a pretty good one. I think its main limitation is that it's only good for small residential. It does not have the capability of doing commercial and even some large residential might run into problems with it.